This video is going to focus on recapping some important fundamental aspects of buffers. But before we discuss buffers, I want you to be aware that there are some other foundational chemistry concepts that you need to know in order to understand this idea of buffers really well. Okay, so some of those concepts are: first, you need to know the definition of what an acid is and what a base is. So if you remember, one of the definitions that you may have learned in your chemistry classes is that acid is any substance that's a proton donor or any substance that loses protons. Base is any substance that accepts protons. So you need to be aware of that definition. And you also need to be aware of the fact that acids and bases can be classified as weak and strong. Usually strong tells you that the dissociation, the extent to which they dissociate into ions is 100% in the case of strong acids and strong bases, whereas in the case of weak acids and weak bases, it's usually less than 100%, usually significantly lower than 100%. So that's an indication that things are weak. Okay, so the word strong and weak has nothing to do with how corrosive an acid is or how not corrosive an acid is. It's something to do with the extent of dissociation. Okay, and it is also important that you're familiar with the strong acids, because the strong acids are only very few, but there are lots of weak acids. So if you know what acids are strong, then it's easy to know which acids are weak. Because if anything doesn't belong to that list, you know that the rest is going to be a weak acid. The same thing is true for strong bases as well. So the list of strong bases is pretty well defined. So if you kind of memorize that, then whatever doesn't belong to that list belongs to the list of weak bases. Okay. One common example for weak acids that you will see in many discussions, and we're also going to use this in the set of videos that follow, is this. One of the examples of weak acids is acetic acid, CH3COOH, which you may have seen in your general chemistry or organic chemistry classes used very frequently. So it's important that you remember that acetic acid is a weak acid. And for weak base, a common example that is used is ammonia, or sometimes they'll refer to this as ammonium hydroxide. So this is a very common example that's used for weak acids and weak bases. Okay, so keep that in mind as we move along. And there will be some numerical problems that we will be doing in the following videos. There we will be using these equations. One equation is for calculating the pH of a medium. If you want to figure out the pH of a medium, you know that it is negative log of hydronium ion concentration or hydrogen ion concentration. Same way, POH is defined as negative log of hydroxide ion concentration. So anything with a P in the front, it's usually on the other side, you're going to have a negative log on the other side. So that's a common feature. So if you kind of recognize that, then you will see that they all follow the same kind of mathematical process. And the last part here, pH plus POH is equal to 14. If you remember, this comes from this concept called ionic product of water. So if you can follow it up and then understand this, this is also very useful, ionic product of water. Okay, so this is an important idea here. And then once you get through this, then you will get into the pH scale. It is important that you know what the pH scale is, what type of pHs are considered as acidic. If you remember, anything less than 7 is considered as acidic. So less than 7 is considered acidic. Neutral, if your pH is equal to 7, then it's called neutral. And then if your pH is greater than 7, it is called basic. So if your pH value is greater than 7, then we're going to call this basic, because these terminologies are going to show up. And if you don't keep this thing in mind about which is acidic, which is basic, which is neutral, then you may end up getting confused. So it's important that you kind of refresh your memory about what these things are. And the other important idea that you need to know is this concept of acid dissociation constant. This is very relevant to weak acids, and many compounds in nature are weak acids. In fact, many biological compounds are weak acids. So for those weak acids, there is an inherent property of how much they dissociate. That is, if the extent of dissociation is quantified by a number, and that number is given by this Ka. And if you remember, this Ka is pretty much like an equilibrium constant. So the more ions you produce, then the equilibrium constant is bigger. So that means Ka will be bigger. If the amount of hydrogen ions that are produced from the acid, they are a lot, then the Ka value is also going to be high. Okay, and this Ka is typically related to this quantity called pKa. So if you want to calculate pK, if you remember, I said anything that starts with a p always on the other side has a negative log, and then you're taking the negative log of that number that you have after the p. So negative log of pk, negative log of ka is going to give you pK. And we know, we may have heard this, that if your ka is higher, you usually think that your acid is stronger, and usually when the ka is higher, the pK value is going to be lower. If the Ka value is lower, the pKa value is going to be higher. So these are some of the things that if you can kind of refresh your memory about, then it will be helpful in the discussion that you're going to have. Okay, so that's an important. These are some fundamental concepts that you need to know before we start talking about buffers. So what are buffers? Okay, so we're going to talk about buffers. So the first thing that you see here is that it is a solution. So that means buffers are solutions. So if you say something is a solution, it's going to contain a solute, and it is also going to contain a solvent. So we're going to take a solute and dissolve it in a solvent, and there is going to be certain things contained in that solution, and that's why it's going to be called as a buffer. So what are the important ingredients in the buffer? So you have a solute, and you're going to have a solvent. Typically, the solvent is water. So water is the solvent. The solute is going to vary depending on what buffer you're going to make. So what kind of things do we think are solutes for a buffer? So the solute, there needs to be, there are two types of solute that need to be present if you want to call a solution as a buffer solution. So the important ingredients that you need to have, or you need to have a compound that is a weak acid, and you need to have a compound that is its corresponding conjugate base. This conjugate base, the conjugate base needs to come from the weak acid itself that we are dealing with. So can we think about a couple of examples? So if you want to think about examples, if you see here we were talking about acetic acid. This guy right here is the weak acid. And then the corresponding pair here, the acetate ion, is called its conjugate base. So if you make a buffer that contains acetic acid and its corresponding conjugate ion, then we can call that as an acetate buffer. Okay. The next set of compound here, if you look here, this is propionic acid. You can see that there are 3 carbons. Anything with 3 carbons, we call it a propane, right? If you remember your alkanes. So this is a carboxylic acid that contains 3 carbons. So it's propionic acid. And then the corresponding conjugate base is your propionate ion. So this is weak acid. This is the conjugate base. Okay. So it is important to realize that buffer is a solution. And if you want to call it a buffer, it needs to have 2 ingredients. One is the weak acid, the other one is the conjugate base. Okay, so this is an important part of buffer. And then, so when you mix the 3 things, that is, if you mix your weak acid, if you mix the conjugate base and some water, eventually it's going to produce the buffer. And the buffer itself, if you put in a pH meter, the device that measures the pH, you will report a value for pH. So the key point here is that each buffer solution that you're going to make has a certain pH value. Then the question becomes, how do we figure out what is that pH value? So if you want to figure out what the pH value is, that you can figure that out by using this particular equation, which is called the Henderson-Hasselbalch equation. So don't forget this. This is a very, very important equation. This is going to show up in many, many buffer calculations. So if you think you're going to prepare for your competitive exams, apply for professional schools and all that, whether it is in pure STEM disciplines, or if you're going into health sciences, it doesn't matter which one you go to, it is important that you know this equation. So if you can memorize it, it'll be very helpful. So what does the equation say? The equation says the pH of the buffer is equal to the pKa of the acid, the weak acid that you're putting in. It is going to have a pKa. So it is that value, that pKa value, plus the log of the square brackets indicate concentration. These square brackets indicate concentration. So it is saying that if you want to know the pH of a buffer, pH is equal to the pKa of the weak acid plus the log of the concentration of the conjugate base that you're putting in plus the weak acid divided by the weak acid that you divided by the concentration of the weak acid that you have in that solution. Okay, so if you knew all these values, if you knew the pKa, if you know the concentration of conjugate base, if you know the concentration of weak acid, then it's very easy to figure out the pH of the buffer. Okay, so this is the key equation. Please memorize this. This will be really helpful when we solve problems because we're going to use it again and again and again. So traditionally, when you solve problems, sometimes the pKa value will be directly given to you, or sometimes they will just give you the Ka value, or sometimes they may not even give you the Ka value. They'll say, oh, they'll tell you that we're using acetic acid in this problem, figure it out, right? But so if you want to figure out the pKa, what you need to do is there are tables of Ka values that are published, and you just look them up. Sometimes you can just, it's as simple as Googling it. You can say, what's the pKa of so and so acid? It'll spit out the number, then you have the value of your pKa. Okay, so this is how you solve this problem of figuring out the pH of a buffer. All right, so now that we know what are the ingredients of the buffer and how to calculate the pH of the buffer, I want to create a visual for you as to how this might work in a lab. So when you try to do this in the lab, what we're going to do is to choose the acid that we're going to use, choose the weak acid that we want to use for making the buffer. In my case, it is acetic acid. And then we're going to pick a conjugate base, which is going to be our sodium acetate, because the acetate ion is the conjugate base of acetic acid. Now we're going to take the two, mix them, put it in a beaker of water, mix it up, get it to the volume that you want, the concentration that you want, and then there we go. We have our buffer. And then knowing the concentrations of the conjugate base that you put in, and then the concentration of the weak acid that you put into the solution, and knowing the pKa of the acetic acid, which is around 4.75, we can figure out the pH of this buffer. And that's how the buffer preparation goes in the lab. Okay. All right. Now that we have made the buffer, we need to know what's the purpose. Why do people actually end up making buffers? The short statement here describes why people make buffers. It says to resist the change in pH if an acid or base is added to the buffer. Okay. So let's try to understand this through a visual process. So what I've done here is going to have shown you two beakers, one that contains pure water, and then the second beaker on the right side, it contains the buffer over here, right? Now to the beaker of water and to the beaker of the buffer, I'm going to do the same exact thing. That is, what I'm going to do is add an acid, a concentrated acid, something like hydrochloric acid. I'm going to add it, and you can see that now we have the same beaker. What we have done here is added 20 milliliters of 1 molar HCl to the water. On this side, we've added the same 20 milliliters of 1 molar HCl to the buffer. So when you add the acid to these two beakers, now we go ahead and measure the pH. When you measure the pH, you will see that the pH of the water has become obviously acidic, and it's shifted to a pH of 1.7. And then on the right side, you can see that in the case of the buffer, it has also become acidic because it changed from 4.75 to 4.69. It went to a lower value. So lower pH value means it's more acidic. It also made it acidic, but you can see that the change is only from 4.75 to 4.69. So if we calculate the difference, and you will see that the change in pH in the case of the water was 5.3 units, whereas the change in the pH for the buffer was 0.06 units. So it tells you that the change in the buffer is much, much smaller compared to what you would see in water, which is not an effective buffer. So as a result, what we are learning from here is that the buffer is doing something to oppose the change in pH. That is, it's making sure that the pH change is not a lot. It's trying to make it a smaller value. Okay, so that's the purpose of a buffer. So just to summarize, so what's the goal of making the buffer? It's useful in the fact that whenever there is a chance that acid or a base gets added to the buffer, it's going to resist the change in pH. It is going to try to make sure that that change in pH is a small value. It's going to keep it to a minimum. Okay, so that's an important aspect of the buffer. Now, the next concept that we're going to look at is what is called buffering capacity. That is, how effectively can the buffer resist the change in pH, okay? And at what pH is it going to be able to do this buffering action? So here, if you read the second bullet point here, it says that the maximum buffering capacity is observed plus or minus 1 pH unit around the pKa of weak acid. Okay, that is, we know that whenever we want to make a buffer, we need two ingredients. One is the weak acid, the other one is the conjugate base. The weak acid that we are using has a certain pKa value. And then based on that pKa value, you're going to have buffering around that pKa value, numerically speaking, 1 unit less than that pKa value and 1 unit more than that pKa value. So how do we explain this? So here I've shown you a table where you have a bunch of weak acids. All of these are weak acids. Everything listed here in column 1 is the weak acid. Column 2 is the formula of those compounds. And you can see that in column 3, we've shown the conjugate base for that weak acid, because whenever you make a buffer, we need both our weak acid and also the conjugate base of the weak acid. And when you have these combinations of weak acid conjugate base combinations, you can see that the Ka for the weak acid is given in column number 4. And we know how to convert the Ka into pKa values. You take the negative log of the Ka and change it into pKa. And those values are reported over here in column number 5. So when you look at these pKa values, so if you decided to make an acetic acid buffer or an acetate buffer using acetic acid and sodium acetate or some form of acetate ion, it's the pKa for the acid that we're using there is 4.75. So because the pKa for that acetic acid is 4.75, if we were to make a buffer using weak acid, the buffer will be really effective 1 unit around that pKa value. So the buffer is going to be effective in the pH range of 3.75 to 4.75. So that's what is listed here. And then, so that means if you're thinking of making a buffer, the first thing that you need to decide is what pH range should I work in. If you want to work in the pH range of around 5, then acetic acid buffer is probably a good choice. If you want to work in the pH range around 7, then probably a phosphate-based buffer is a very good choice, because then the pKa for that is around 7.21. Therefore, the effective buffering range is going to be between 6.21 and 8.21. So it's going to be very useful in that range. So if you want a still higher pH, then you use the boric acid buffer. If you want to go even very high, much higher, you can use ascorbic acid as a choice for buffering compound. Okay. So what this is saying is the pKa of the weak acid plays a very important role in deciding in which range your buffer is going to be really effective. So now the question becomes, why is that pKa value so important, and what does that actually give us? Okay, so to understand this, I'm going to create a visual for you, which comes from knowing titrations. Okay, so you've probably learned about titrations in your general chemistry class. So now we're going to do a titration of a weak acid. The weak acid that we have chosen for our experiment is acetic acid. So we have chosen that. So we're going to do a titration. So when you do a titration, your setup is probably going to look something like this, where you have a burette. It's filled with sodium hydroxide. Here is our acetic acid in the conical flask, in the Erlenmeyer flask. And now we're going to start slowly adding NaOH drop by drop by drop. And then we're going to neutralize the acid. But as we are doing this, I'm also doing one more thing, which is I've connected a pH meter that dips into this solution. The pH meter is going to keep recording the pH value right over here. And as it is doing this, I'm going to plot a graph with the volume of NaOH on the x-axis over here, and then the pH of the solution on the y-axis over here. And I'm going to plot a graph of this. If I plotted a graph, you're going to see this green line pop out. And this line indicates how the pH is changing as we are adding more and more and more NaOH. Okay, so here are a few things that we have when we can learn as we look at the titration curve. The first thing to note here is that the curve is starting to go up like this, and then it's sort of becoming flat over here, and then again it's starting to increase steeply over here. So this tells you that in different regions of pHs, the change in pH values is actually different, in the sense that the slope of the line is very, very different. And this is going to be important for us in the discussion that we are going to have. Okay, so before I get into the slope discussion, I want to tell you a few things about the titration curve itself. In the titration curve, you're going to, when you start your titration, your pH is going to be somewhere around a 2, and that's where we're going to start. So at that stage, what do we have in the reaction? In the reaction, what we have is this acetic acid present in the conical flask. we have not added our the sodium hydroxide yet. And even though we have not added some sodium hydroxide there, you're going to end up having a small amount of acetate ion in the solution because our acetic acid is a weak acid. So what we're going to see at pH 2 is almost close to 100% is weak acid. Maybe a small percentage is going to be your conjugate base, and that's going to be the status when you begin your titration. Now, as you continue to add drop by drop by drop of this sodium hydroxide into the beaker, and you keep stirring it and you keep recording the pH, this curve is going to start growing from here, and it's going to keep going like this, like this, like this, like this, like this. It's going to keep going like this. And as it is going, and you can see that the pH is increasing quickly, with this as a higher slope here, and then it starts to slow down right when it gets over here, and then you can see that the slope gets slower and slower here. And in that range, it's not changing a lot. It's changing, but it's not changing as quickly as it was changing right over here. Okay, so what is happening over there? So as we keep adding more and more NaOH, what is happening is our pH is getting more and more closer to the pKa of the weak acid. And the weak acid in this case is acetic acid, and you can see that the pKa for that weak acid is 4.75. And as the pH got closer to pKa, what we end up having there is 50% of our weak acid and 50% of conjugate base. That is, because we are adding sodium hydroxide to the solution, we are deprotonating this hydrogen, and then we are increasing the concentration of this acetate ion. So at this point, when the pH gets equal to pKa, you have equal concentrations of weak acid and conjugate base present in solution. But if you go beyond that and you continue to add more and more of this NaOH, at some point you're going to end up completely neutralizing all of the acetic acid, and that's where we reach the equivalence point. When you at the equivalence point, you have no weak acid left. Everything has been converted into conjugate base. Okay, so this is what is happening in the titration curve. But the most important thing to note for us here is that from the perspective of the buffer is we know that buffer is any solution that is going to resist change in pH. So if you want to bring that thing into context, if you look at the titration curve, the place where we are seeing very little change in slope is this particular region over here, the one in the orange colored box. In that region, the pH is not changing a whole lot, and that region is centered around the pKa. So if you go 1 unit on the pH scale above the pKa or below the pKa, what this is saying is that your pH is not going to change a whole lot, and that will be the ideal region for making the buffer. So this is the reason why the pKa of the weak acid is very important, because right around when your pH is exactly equal to pKa, right around that point, you have a pretty good buffering capacity where you have 50% weak acid, 50% conjugate base. And as long as you're within 1 unit of pKa, 1 unit of pH around that pKa value, you're going to have pretty good buffering. So that's why this range, 3.75 to 5.75, is called the effective buffering range or buffering capacity for the acetic acid, sodium acetate buffer. If you are going to prepare the acetic acid, a buffer containing acetic acid and sodium acetate, then that buffer is going to be pretty effective in the range of 3.75 to 5.75. Okay, so that's why this pKa is pretty important. Now we've talked about all the key aspects of the buffer. There's one final point that I want to make in the sense that this idea of buffering is important in all kinds of reactions that we do on the lab bench or inside living organisms. In all of those cases, buffering is very important, because first of all, in the case of biological organisms, it's important to realize that we are predominantly made up of water. 70% of our body weight is made up of water. And it's not that our body, yes, it contains water, but it's not pure water, in the sense that water is mixed with a bunch of other compounds. Some of them are going to be your weak acids and conjugate bases. So as a result of this, the solutions inside your body are usually buffered. And because they are buffered, then buffer being there, as we said before, it is working to keep the pH change minimal. Now the question is, why is this important from the context of biological reactions? The reason why this is important is inside our body, inside the cells of the bacteria, inside the cells of the yeast, all these kind of organisms, you have water present, and many chemical reactions are happening in there, and the environment in there is buffered, and this is very important because the different chemical reactions that are happening inside the body or inside the bacterial cell, they are happening at very, very different pH conditions. So for example, if you have a digestive enzymes acting in your gut, those are active only when your pH is very, very high, like pH around 2. So that means your pH there has to be buffered around a pH of 2. Then if you go a little bit downstream in your gut, there the optimal pH required for functioning of those enzymes is pH 7. So the buffering action there tries to make sure that the pH doesn't exceed that range, so that if it exceeds that range, then your enzymes are going to not work. If you want your enzymes to be working, then you want to make sure that the pH ranges are maintained. For that purpose, the buffer is going to play a very, very important role.